So, welcome back on the course on optimization techniques for digital VLSI design, and at present we are in module 4 on testing. So, if you recall the last lecture, we were discussing on the basic preliminaries which are required to cover the advanced optimization techniques for test pattern generation and testing of digital VLSI circuits. So, in the last lecture basically that is we are in the set of preliminary lectures. We have discussed about basically the basic idea of VLSI testing, test pattern generation, and basically what are the fault models and what are the optimization techniques required so that we can test fairly complex circuits. And the motivation was to build a background of testing of circuits which are actually at the level of systems, which are slightly lower complexity from the level of systems, and then when we will be going through the lectures 3, 4, 5 and 6, which will be building on the basis we are trying to develop in lecture 1 and 2, how they can be optimized so that we can handle larger circuits. So, in the last lecture basically we covered the testing required or the test techniques required for handling combinational circuits. Now, basically we will be discussing about sequential circuits. So, what we discussed in the last day, that to handle complexity of even a fairly simple circuit, simple in the sense that it is lower complexity than NOCs and SOCs, to handle even a VLSI kind of a circuit like a multiplier or a simple MIPS processor. So, what is the level of testing we require? We actually have to handle the circuit not at a functional level, we can handle only circuits from a level of fault models. So, fault model idea is that we say that some of the lines can be stuck at 0 or stuck at 1. So, that is basically the fault model, and we have to generate test patterns so that we can verify that no such faults are present in the circuit. So, basically this is an optimization step. What it compromises? It compromises that now the quality of assurance you can give to the people is not exactly same as the functional test. It will be slightly lower than that, but actually fault model, the gain we have seen is that the number of test patterns required are exponentially less than required for a functional level of test, but the quality of assurance is near about the functional test, which has been found out by statistical testing of large number of circuits. Now, we will see what are the challenges we face when you go for sequential circuits, because most of the circuits basically nowadays are sequential. Very fairly you will find circuits which are purely combinational in nature. So, what was the basic assumption we learned from the last lecture? That we are going to go for structural test, and that also with fault models. That means we will be, and also our assumption is that we are going to take stuck at fault model. Stuck at fault model means each line can be either stuck at 0 or stuck at 1, and we are going to take only one fault at a time, and we have to verify that by a test pattern that fault is not existing in the circuit. If we can do it for all such faults, then we will say that fault coverage is 100%, and then the circuit can be shipped to the market. And statistically it has been found out that if you do such a kind of test, then the correlation with functional test is more than 99% plus. Now, we will see the challenges for a structures of such a testing for a sequential circuit. Actually, we will now be able to appreciate that whenever we go to sequential circuit, the complexity will actually blow up and it will become a more difficult problem to solve. So, in the last class, we have taken different circuits, and then we have seen that there are two ways of test. One is actually called the random pattern test, and another is called the basically the sensitize, propagate and justify kind of test, where difficult faults are tested. So, when we are talking about sequential circuits, we will be mainly focusing on sensitize, propagate and justify approach, because mainly the difficulty or the complexity starts when we are going for such difficult to test faults. So, for example, now I have taken a simple sequential circuit, you will be able to appreciate that we have a flip flop. So, one thing just I would like to say that in case of circuits, generally when you are going for large scale circuits, we generally talk about D flip flops only. Anyway, flip flops are interchangeable and the theory will remain same, but for most of the implementations we generally use a D flip flop. And if you have forgotten your digital fundamentals, just a recap that D flip flops will take the value from here, from the input to the output in a clock edge. So, that is what is the idea. It is a simple D input and you will take the value to the output. Now, let us see that this is your very simple sequential circuit, and we want to go for testing a stuck at 0 fault here. So, we will see what is the complexity involved and how it becomes more difficult in a sequential circuit like this. So, now one very important thing you have to remember, that when you power up a circuit, the value of the output of the flip flop may be 0 or 1. It is totally undeterministic, non-deterministic, that whether it will be 0 or it will be 1, we cannot predict on the power up. It can be any arbitrary value. And as we do not know what is the value and there is no provision of measuring, because as I told you, this is the input side and this is the output side. You can either apply some patterns here and you can probe the values here. That is again another advantage of structural testing using fault models. That is, you do not require any probers inside the circuit, which is a very difficult problem, because bringing so many pinouts of a circuit is a very difficult problem. So when we say X at the output of a flip flop, which is always in the startup of a sequential circuit, that we cannot predict whether the output is 0 or a 1. So now anyway, so that fundament is gone, we do not know whether it is a 0 or a 1. So I have put an X, and then basically so this one will also be X, I do not know what is the value, this one is also going to be X. Now we know that it is stuck at 0 fault. So what we have to do, we have to put a basically a 1, that is the sensitization step. So what is the value? The value here is D, that is normal case 1, failure case 0, that is very obvious. Now let us make it slightly clear the figure. So this is what is required. So this is now the case. Now obviously the X, because this is a OR gate, so we have to make the X equal to 0. In fact basically we require a 0 over here to do it. Now this is where the complexity increases compared to a combinational circuit. If it is a combinational circuit, basically this line will be cut and this will also be a this line will be cut and this also will be a primary input. So very easily by this will be let me go in steps. So basically let us try to not jump the steps basically. So the idea is that stuck at 0, I put a 1 over here, now I require a 0 over here and the value will be propagated. So if it is 0, so the value will be a D over here, normal 1, faulty 0, and this D will be propagated over here. That is what is the requirement. This is sensitized, the value is propagated over here and the value of 0 here is the justification. That is done. But now the problem here is that all other things will be simple, D I am putting over here, D I am putting over here, but how do you put a 0 over here, F? That is a very difficult problem, because when you start up the circuit, the value is 0 or 1, I do not know. That is why I have written an X. So basically this line is also X and now I require to control it. Now you can see there is no way of controlling directly line F or even line C, because it is a flip flop output and the startup of the circuit will make it as a 0. Then what I have to do? So that is the difficulty of sequential circuit testing, because if it has been a combinational circuit, this would have been a primary output and you could have directly put a 0 over here and your job would have been done. Basically in a combinational circuit, this one would not have been there, this is a primary input and D will be a primary output. So now the problem of sequential circuit increases because of flip flop, the controllability problem becomes more difficult. Like in combinational circuits, the line F or C would have been a primary input and you could have directly put a 0 over here. But now as is a sequential circuit, X, that is line F and C, are output of a flip flop and it is a non-controllable line directly, which actually makes the problem very, very difficult. Now you can understand there is only one flip flop at the level 2. 1, 2 and this is at the third level is a flip flop. But if you can assume a very complicated circuit, then there will be flip flops at all levels and hundreds and thousands of flip flops will be there. So you can think how difficult it is to control them. But in case of a combinational circuits, you can directly control them from the primary inputs, because there is controllability and there is no feedback from any flop. So that is what makes the problem very challenging. Now how do you do it? So of course I require a 0 over here, that is my primary requirement. I require a 0 at the output of the flip flop. So how can I do it? So and obviously in sequential circuits you cannot test by one test pattern. Like in combinational circuit, it was very obvious and also you have seen by example that for a given stuck at fault, you require maximum one test pattern to test it. But in case of sequential circuit, the philosophy will not hold, because first you have to make the flip flops controllable to the respective required value. Like for example at X, I require X is equal to 0. So first I have to bring all the flip flops to the required value and then only I can apply the test pattern, which in this case is A equal to, this was the case basically, which is A equal to 1 and the final value has to be propagated to the output. B is not required in that case, this is X. So basically the test pattern A equal to 1 can only be applied after the flip flop has been settled to 0, that is X is equal to 0, then only you can apply the exact test pattern, which is A equal to 1 and the value will be propagated to the output G, which is D. So in case of a sequential circuit, all the efforts will be required to control the internal lines to the required 0 or 1 based on ATPG, which is the output of the flip flop. That is the main challenge of basically a sequential circuit compared to a combinational circuit. So how do we require a 0 over X? How do you get it? Basically in this case it is simple. You can this one is already X, we know, we do not know what is the value of the output of the flip flop as startup. But fortunately, if I make b equal to 0 and this is an AND gate, so AND of x and 0 is a 0, so it will become a 0. So this is a good value in this case, which make it basically a 0 over here. So if 2 would have been an OR gate, the problem would have been more difficult in this case. So anyway, I put b equal to 0 and then d will be 0, then I will apply a clock pulse. So the first pattern is x equal to 0 and a equal to x. I do not care about the value and I put b equal to 0. So if b equal to 0, output of gate 2 is 0 and then I apply a clock pulse, then automatically the x is going to become a 0. So this first step is actually controlling the value of the flip flop. So this is an extra test pattern required if you want to go for a testing of a sequential circuit. So this is one flip flop, so I have required one extra pattern. If there are n number of flip flops at n different levels, in the worst case you will require n different patterns to get them settled at the value. So for testing one stacked fault in sequential circuits, you require a huge number of test patterns to actually settle the flip flops to their required values, then only you can do the test. So you can understand how the complexity starts rising. So now what I have done, in the first case I have applied a equal to x, b equal to 0, x means it can be anything, then the value of d becomes 0, you apply a clock pulse, then x is going to become 0. So now your f is 0, c is 0 and basically your d is 0, q is 0, the q is 0 by the previous step. So now I am getting the controlling value f equal to 0 at gate number 1. Now I can apply the real test pattern, which I am applying a equal to 1. Now the output will be going to the output of flop and it will be going to output of G, which is equal to D, and your job is done. So this case is very similar to a combinational test pattern. The idea is, if all the flip flops are set to their required values, which is required to do the testing, once you have settled the flip flops to their values, after that the testing of the fault will just become a simple automatic test pattern generation problem of the combinational circuit. Like if when f is made 0 by the previous step where b was made 0, now it becomes a combinational circuit problem. That is, you have to apply a 1 over here, it is sensitized, d, t is propagated over here, and already you have justified it previously by making f equal to 0. So in sequential circuit it is slightly the other way around. First you make everything justifiable, then you sensitize and propagate. So more complex. Here justification you have to plan beforehand, because most of the lines will be uncontrollable in this case directly. So you have to settle the flip flops so that all the lines are justifiable and propagatable, and then only you can go to the previous step. So let us make the things more simple to understand, that here all lines are not controllable directly because they are flip flop outputs. So whatever control you want to require, you have to settle the values in that manner using a previous sequence of patterns to get the flip flops to the required values, and then you can apply the test pattern. Now how to solve the problem? So basically this is just the idea of a flip flop, just you can see, I will come to this slide in a few minutes. So what is the problem now? The problem compared to combinational circuit is that you require more number of test patterns to test a single stacked fault. That is where optimization is again coming into picture. Even if it is a very small level circuit where you have 100 faults, to test a single fault, if you require 10 or 20 patterns, to test 100 faults it will be in the level of 1000 patterns, which is not at all possible even for a medium scale integration circuit. Forget about NOC and SOC. So we require that our complexity should not grow more than the complexity of testing a combinational circuit. Combinational circuit testing, what we have seen, that even if there are 2n stacked faults, the number of test patterns will be much less than that, because one test pattern will cover multiple faults. And not only that, basically for one pattern or one fault, maximum one test pattern is required. That is the worst case. But in this case, as you can see, the things have started blowing up. So how to do it? So one way is that we all might have recalled in our digital design lectures that all flip flops have basically something called a set and a reset line. So if there is a set and reset line, then the advantage will be, in that case we will not be able to have to back propagate and actually give the settling values to the flip flop, like in this case which is stacked 0. Sorry, in which case f is required to be made 0. If you have a set and a reset line over here, then you can make the reset line equal to 1, means enable the reset line, so automatically your E will be equal to 0, and you do not require an extra test pattern like b equal to 0 in this, b equal to 0 in this case, to make the E equal to 0 or in turn f equal to 0. Basically you can directly make the reset line equal to 1, so that directly it will become 0 and you can do the job. And the advantage here will be, if even there are 200, 300 flip flops, all the set and reset lines will be controlled separately and they can be brought to their required values. So you require just one clock period, or you just require one test pattern to set and reset all the flip flops as required by the test pattern. Like in this case you require it to be 0, so directly you can set the reset line. If there is some flip flop whose output has to be made 1, you can make it the set line equal to 1. So basically we will go by this architecture. That is, we have set and a reset line. So, when you directly control set and reset line, basically the inputs are do not care and you directly get the value. And one thing, we cannot make set and reset line equal to 1 together, which is illegal, but for all other cases, if you make set equal to 1, the output equal to is q equal to 1, if you make reset equal to 1, the output equal to 0, and other is a normal D flip flop operation. So, you can do that. So, the same thing they have shown. I am just taking another simple example to see if you have a set reset, what will be the advantage. Like in this case, it is a stuck at 1 problem fault. So, you will require a 0 over here. So, if you have a 0 over here, basically, then maybe I assume that it is a XOR gate. So, if I assume that I require a value of 1 over here. So, 1 and a 1, normal case the answer will be a 0, but if it is a it is a normal case the answer is a 1, because 1 and 0 the answer is a 1, but in the failure case the second line is stuck at 1, the other input is 1. So, 1 and a 1 same value XOR gate, it will be 0. So, the output will be D. So, something I require like this. So, this may be one test pattern. So, basically sensitize, I propagate the value through this, because there is only one output which has to be value has to be propagated to the input of the D flip flop, because there is only one output. But actually more important point here is to note that I require the value of 1 over here. But again, as I told you, directly you cannot control it, because it is a flip flop pattern. And now in this case, if you see, I will just give you as a homework, you can just say that I require to make this line as a 1. But you will find out that in the startup this line is going to be x. So, unlike this previous problem, where it was very nice that if you apply b over here, this line is becoming b and is solving your problem, but in this case there does not exist any input which can directly control it to 1, that you are not able to do it, you will not be able to do it. You can take as a homework and see that there does not exist any pattern over here, which if this is x, you can directly make it as a 1. So, in fact, this fault will become an untestable fault. So, that means indirectly this line will not be able to be controllable, and this fault will become untestable, which will be a very bad thing, because your coverage will come down. So, basically now I have to use set reset line. So, here I will make the set equal to 1. If you make set equal to 1, directly the output will be 1, you will get a 1 over here, and then basically as I shown you, basically I apply a 0 over here. So, normal 0, fault 1, so this is D prime, output will be D, and finally you will get the value of A. Importantly is that I actually I made set equal to 1, so that I get the 1 and I have controlled the flip flop. Now, once the flip flop have been set to the required values, I put set equal to 0 and reset equal to 0, because I want normal operation of the flip flop. So, now again D has been propagated, then I put a clock pulse, your output of D will be here. So, if the value is 1, circuit is normal, if the value is 0, there is a stack at 1 fault over here. So, what we have seen that without set reset your problem is going to blow up. So, we require a optimization step. So, what is the optimization people have done? They have put set and reset. Now, this is again going back to the old ball game to square one, that is of structural testing with extra pinouts. 2000 flip flop means 2000 set reset lines has to be brought out as pin. So, again we are boiling down to the same old story, that to test the sequential circuit you have to control the flip flops. If you do not control the flip flops directly, then lot of test patterns have to be applied to make the flip flops settle to the required values. And this is an example of an XOR gate where you cannot even settle the flip flops to be made the line to be 1 to 2. So, the fault will become an untestable fault, which is a very catastrophic situation. So, in such cases flip flops has to be directly controlled. How you can directly control a flip flop? By putting a set and a reset line. If you put a set and a reset line, what is going to happen? As I told you, huge number of extra pinouts will be there, and the story will be again big flop, and we will again back to square one, which was actually the testing of combinational circuit at structural mode without any fault, a lot of pinouts. So, this story was also had come to a catastrophic end. Then there is something revolutionary that happened, which have made a phenomenal, just like testing of circuit fault model was a phenomenal jump. Now, I am going to tell you the story of a scan chain. Actually, we again made a phenomenal jump in testing of circuits, and it made the testing of sequential circuits a very low complexity problem, just like stacked fault made the story of number of test patterns and pattern generation complexity come down to a drastic level lower bound. So, same thing actually happened for sequential circuits when people started using a scan chain. Of course, with little area overhead. And one beauty is in case of fault model, you might argue that actually I am not going for functional test of the circuit. So, there is slight quality compromise in the level of test, but in case of scan chain based testing the complexity has been lowered, but there is no quality compromise in test, because we are not compromising in any kind of fault model, nor we are compromising in the number of test patterns. But what is the slight compromise? We slightly increase the area over it. So that is very well accepted. So scan chain you can think is a big thumbs up when you are going for testing of sequential circuits. This is actually revolutionized, and in fact as it's a cramped up series 2 lectures of cramped preliminaries of testing. I am not telling the intermediate steps, because there are a lot of intermediary words, mathematical formulations, which you can find in any course on CAD for VLSI, that how people have come from the set reset problem to a scan chain. There is a lot of story in between before reaching to this final solution. But as we are covering up in 2 lectures, so we are cramping it up. So now just I will tell you, I will come back to this slide later, because it is the architecture of a scan flip flop. Let us just try to tell this story. So now what is the problem? So you have 10 flip flops. So you have to control the 10 flip flops. One way is that you can use test patterns and backtrack and all these things you can do, which is a long story, or you can use set reset. Another thing people thought is that if somehow I can cut out the combinational part for some amount of time, and if I can connect the flip flops in series in a chain, then I can actually directly put the values. Again, let me tell you this thing. So if you look at this circuit, this will make the things more clear. Say for example, if I look at this circuit, this is the circuit. So what I want to do is that, say somehow for some part, say if I can somehow cut out this circuit, and then if I can directly put some value over here, then my job will be done. One way is of course set and reset. This is also you can do, but in that case if I say that I will put if the flip flop is there, I need, obviously whenever you have to go for an indirect control, you have to put a multiplexer, that you have already seen. So this one will be your normal D input, and this you can say that I will bring some value from the output. This is 0 and 1, this is the mode of test. So if you make the mode of test as 0, so the D will go as the input to the flop, and if you make mode of test equal to 1, the output value you can put it and directly control the flip flop. So anyway, so this is fine. So you will require a lot of pinouts. This story will remain same like a set reset problem. But that is what is required. Basically also you can cut it out. Then also you can actually control the flip flop directly. Now, but the problem is that I cannot have extra pinouts. So what I can do? So then people thought that some story like this, that for example, I'll just take a slightly complex example and I'll come. Say let is a slightly complex figure. So now what is the requirement? I'll just zoom it slightly. So you can just see this is the figure, slightly complex level 2 flip flop. So what you have to do? You have to control these 2 flip flops to do some testing. So somehow what if I can do is that if I can cut this, somehow if I can cut it out, okay, and if I can somehow make a boundary something like this, then I will be very happy. So what is the boundary? Slightly I have made a mistake in the boundary. I have to just eliminate out these 2 flops. So what is the boundary story I am telling? So if I can somehow cut these 2 flip flops out. So now what is happening? Whatever is below this red line, the 2 flip flops will be out. So that is what, then I can directly give some value over here, and also I can give some value over here, and I can do it. But again, if you want to directly give some value, you require a multiplexer anyway, but you have to use 2 pins to do it. That will make the problem slightly difficult. Then what is a scan chain? The scan chain says that I will not put too many pins out. What I will do is that I will actually cut this out, then again I will cut this line as output, and again I will cut this line as output. So basically these 2 flip flops are isolated. Now I will not put any direct control over this input, because if there are 10 flip flops in sequence, then you have to put 10 control lines. Rather what I will do, I will put the output of this flip flop like this, the output of this flip flop, and I will connect it to the input of this flip flop. That means I will try to make a chain, like for example these are say 3 flip flops, which I have now isolated from the normal circuit. So this is one input of the flip flop, the output of this flip flop I will connect to this, the output of this flip flop I will connect to this, and if there is another flip flop output I will connect to this, and finally I will make it out. Of course, you have to remember that there are flops there are muxes over here, which is actually going to take 2 inputs. One input is basically the normal input from the circuit, the other input is through a chain. So therefore we actually call this technique as a scan chain. So what you do, by multiplexing arrangement, you cut out the circuit into parts. So one part, the combination circuit will be out, and all the flip flops will be connected in a chained fashion. Like output of this flip flop will be connected to this, this is the output here, but if there is another flip flop would have been here, the output will be connected to this and will go for. And whenever the circuit will become normal or in normal operational mode, all these scan part will be disconnected and the circuit will be operating in the normal mode. Now what I have basically, I have something like a single chain like this. This is the chain of flip flops. All these are connected in a mode. This is one primary input and there will be one output. Now this becomes a shift register. So once it becomes a shift register, maybe if I require the control of 1 0 1 1, you can easily send a sequence of running ones and zeros of this and you can fill up the shift register chain. So now the problem has been solved in a very simplistic design manner. In case of VLSI, always you have to remember that complex designs are complex, but the solutions are very simple. So if you make a solution very complex, the hardware area will be higher, power will be higher, and the problem will not be a very good solution. Here the problem is very complex, that given all the flip flops integrated in the very internal parts of the circuit, how you can make the values 0 and 1 controllable with the minimum number of pinouts and minimum amount of time. So what they are doing over here? With multiplexing arrangement, they are cutting out of all the flip flops, but they are not bringing primary input and output of all the flip flops to the primary input output. Rather, there is only the extreme flop output will be the primary input and the output of this one will be connected to the input of this flip flop, the output of this flip flop will be connected to the other input and it will made a chain. So it will become a shift register. So wherever you want to make 1 0 and 1, you can just make this running sequence and you can just load the shift register using the sequence and a clock. So that is a pure very simple second year digital fundamental. You can easily apply this and you can set the flip flops this one, and then again you can bring it to the normal mode and to the test. I will give you an example to show you very explicitly, but I have just given you the idea. So what problem we have solved? So all the flip flops now will be set. There will be only 2 lines extra, one is the scan in and one will be scan out. But now you can say that, and if you tell me how many test patterns are required, there will be mainly for 2 test patterns. One pattern will be required to set the flip flops to different values required and one pattern will be required to do the test, that is the practical test. But now test time will be slightly increased, slightly or rather it will be increased to a great level. Why? Because one pattern will be required to do the test, but now all the flip flops you are connected in a sequence. So you do not have direct access to all the flip flops to set or reset depend on the requirement. Now what is going to happen? If there are 100 flip flops in a chain, you require 100 clock pulses to shift the values of 0 and 1 to the shift register to get the value. So test time will be increasing. Pinouts will remain same. The number of test patterns is also 2. One is the test pattern to do the test, another is the sequence to be entered. But the sequence to be entered basically require lot of time, because if there are 100 flip flops in a chain, you have to go over there. So this story was fine when you are having medium scale or slightly higher scale of integration. But as we will discuss in the end of this course, end of this lecture today, will motivate, you will automatically be motivated that if there are 20,000 flip flops, to test one circuit, you require 20,000 clock pulses to settle the different values of the flip flops, which is going to be very problematic situation. So when we are going for NOC and SOC, this scan chain has to be optimized. That is what we are going to learn. So anyway, so I think I have given you the motivation. Now I am going to give you a very abstract view. So assume in this case there are 3 flip flops 1, 2 and 3. These are the secondary inputs. Basically they are outputs of all the flip flops will be connected to a combinational cloud, and they are also in the input from NSF. NSF means the next state function block. Basically it is a combinational circuit. Output of the flip flops are all going to be feedback. Basically this is your combinational circuit NSF block. So basically all this generally feed it, and the output of the flip flops anyway again go to the combinational cloud, that is basically your NSF block, and then actually this is what is a typical structure of a sequential circuit. So I need not draw over this, but now basically say that somehow I need to make it 1, 1 and 0. I need to do that. So basically what I will have to do, either I have to make that set reset. So in this case 6 lines will be output, but you can set and reset in one go, because this is set, this is set and this is reset. So if there are 1, 2, 3, 4, 5, 6 lines directly as output, you can do it in 1 clock pulse by making the set equal to 1, set equal to 1 and here reset equal to 1, your job will be done. But in fact that will actually blow up the number of pins, because 6 additional pins will be required. So that is a very difficult problem. Now let us see how scan chain actually solves it. So assume that there is a combinational circuit over here which are actually feeding this D flip flop. Now somehow I have to cut this. So how I can cut it? I have to put a multiplexer over here. So they have put a multiplexer. There is one pin from the combinational part, that is the NSF block, and the other part actually basically follows from the output of the other flop to this, other flops to this. So you can see a chain has been formed, that is this one. So when these flip flops are in scan chain mode or a test mode basically, so you can see the this is the primary input and this is one primary output. This is scan out, this one will be an additional primary output. Only 2 extra pins are there. So now you see all the NF shape block has been decoupled. So all the flops have been separated out as a separate chain. So how it happens basically? This you can see I have made a chain. Say as I told you, what was the value we required? 1, 1 and 0. We require 1, 1 and 0. So what you will do? You will put a, first you will put a 0 over here, you will give a, sorry, first you will put a 1 over here, you will put a 1 over here, scan in and you will give a clock pulse. Of course, the 1 will appear over here. Then again you will put a 1 over here and then you give a clock pulse. So once, see the second clock pulse, what is going to happen? This one will be propagated over here and this one will come over here. Next what you are going to do? Next you are going to give a 0, next you are going to give a 0 at this input and give a clock pulse. So what is going to happen? This one will be propagated here, this one is going to be propagated over here, this one will be going over here by the chain as a shift register, and this 0 will basically, this 0 is going to be appearing over here. So you get it settled. Simple shift register fundamentals. So 3 clock pulses, your pattern is applied. So this is set, take the flops. So you assume that if there are 10,000 flops in a chain or in a circuit you have to make a chain, then 10,000 clock pulses will be required to settle the flops. So this actually not increases the number of test pattern, but it actually delays the amount of time to do a testing. So this, if the flops, so when it was a medium scale circuit or to typically slightly larger scale integration, people still tried to handle this complexity by increasing the flops to scan chains to multiple number of partitions. That I will not have one 10,000 length chain, rather I will have 10 chains of 1,000 length each. But in that case, what is the penalty paid? You will have 10 extra pin outs for scan in and scan out, because of course you have to have a scan in and scan out for every chain. But if you want to control the chains parallelly, so more pin outs should be there. So that is actually some kind of optimization to handle test time that started taking place. All these things we will start discussing when we will be going to the original part of the course from the next lecture series. But this single scan chain actually solved problems till many years before moving to more complex circuits. Because as you can see, as is a simple scan chain or the simple register, so the delay is very less, because one flip flop will be connected to the other will be connected to other and so forth. So from the digital fundamentals you can apply very high clock speed to transfer the data, because delay is almost very negligible, because one flop to other and so forth. There is no commercial circuit in between. So the scan data can be fed very fast. And now when the scan job is done, basically you can see the flip flops are in original mode. So you can see now the scan in and the output of these, all these lines are cut. So lines from the combinational circuits are NSA block is all coming to the flip flop. That means the circuit is now operating in the normal mode. At this step you have to particularly apply basically your test pattern and you are going to do the job. And even if the circuit is operating under normal condition, you will be in this mode only, where all the circuit is in the normal mode. You can see that all the inputs are going from the next state block to the flip flop and you are doing job. This scan chain is a cut mode. So advantage, you can do the testing with only 2 extra pins. Penalty paid is you have to put some multiplexers. Anyway, I am not too much bothered about area these days, but only challenge that remains is the test time. So that has to be optimized. People started it optimizing when they have gone for advanced level of testing for more complicated circuits. So all these things we will discuss. How to do this will be a major part of the course, will be in the forthcoming lectures. So now let us look at the typical architecture of the scan. So what it happens basically, we have a D flip flop, we have a multiplexer, this is the normal input and this is the scan in. Scan in means it can be a primary input or it can be the input from the other flip flop which is previous to that in the chain. And so we represent it something like this. We say that this is a scan flop when the mode is a normal mode. Basically this normal input will be there, the scan in will be not there, and basically vice versa for the test mode. So we represent a flop in this way as a scan flop. This is a special kind of flip flop where you basically have a multiplexer, and with the normal input you also have a scan input and a mode to control this. So in most of the VLSI circuits, most of the flip flops, if you see, you will be surprised that all are scan flops. Because scan chain is a de facto standard that has been coming into picture for all circuits. Nobody actually uses a normal flip flop. So if you have some experience in designing CAD circuits, you will be surprised that all the flip flops basically are scan flops, because area nobody bothers much, but the only way to get access to circuits inside is a scan chain. So even you will see that even if you are going from NOC and SOC, to get to the internals of the circuit you should have a scan chain. Of course lot of optimizations will do, like breaking the single scan chain to parallel scan chain, and then some part of the scan will be dropping because you have to slightly compromise the area or test time to slightly lower the complexity to have a faster test time. So all those compromise will do to optimize the test time, or minimum amount of compromise to get a greater benefit in terms of test time and efficiency. But Scan chain will still be the de facto standard to go to the internals of the circuit. Fault model will be still the de facto standard to go for testing. Of course, it may improve from stacked to bridging, etc., but still the story will remain same. So when we will be talking about optimization, means what are the advances that this whatever we are discussing till now is something called the CAD for test, which applies to typically complex circuits like minimum scale processors. But when we move from processors to NOCs and SOCs, the time will be very high because the circuits will be very high. So this simple way of test will not be applicable over there. Even if you apply, time will blow up. But still we are doing as a prerequisite because the bottom philosophy remains the same: fault models and scan. For sequential circuit, you should have scan to go into the circuit, and fault model, the philosophy of fault model is mandatory to do test in a reasonable amount of time. So whatever you do, these things has to be done. So now what? Now basically we are going to see with an example how scan has to be done. So we are taking a very simple circuit and we are taking a stacked 0 fault over here. So same problem as you have seen, there are 2 flip flops in chain in sequence, you have to do that. And we are not having any set reset lines because that will blow up the problem. So simple, first you have to do an ATPG. So what are the steps? Now I am going to take the things more mathematically, that what are the steps to do it. First basically you have to forget that there are flip flops and you have to go for an ATPG. So I just say that there is no flip flops over here. Just assume that they are directly connected. For timing you just assume that. So what will be the, I am making a pure combinational circuit by removing all the flip flops, connecting the input to the output, and your job is done. Then go for ATPG combinational. Stacked 0 means sensitize, put a 1, normal 1, fault 0, D, output will be D, that is the propagation, because there is only one path here, propagation is done. Now I have to justify. So how you justify? H, output of another input of an OR gate, obviously it has to be 0 to make it controllable. Inverter, so I have to put a 1 over here. Next I have to apply a 1 over here, this is AND gate, so A is obviously equal to 1. So now G is equal to 1, H is equal to, my job is done, again I have to go back, this is the AND gate, is this AND gate, basically I am talking about this AND gate, so the output of the AND gate is required to be 1, so of course B equal to 1 and C equal to 1. So just see, if A equal to 1, B equal to 1 and C equal to 1, your job is done basically. So 1, 1 and 1 means basically the output of this gate, that is this second AND gate is going to be a 1 because A equal to 1. Sorry, B equal to 1 and C equal to 1 implies the first AND gate is a 1. So this gate is this line is basically 1. Then A is also equal to 1. So the output of the second AND gate is equal to 1. So basically stacked 0 fault is sensitized, and then we are propagating it to the output D. Basically H is also equal to 0. So the D will be propagated over here. So this H is equal to 0 implies that G is equal to 1, and G is of course equal to 1 because B equal to 1, C equal to 1, your job is done. So the sequence of combinational test pattern is 1, 1 and 1 and the output is D. Now I have to apply it. So here this problem of sequential circuit starts coming into picture. So I know that A equal to 1, B equal to 1 and C equal to 1 is going to serve my purpose. But at the same time, so I am slightly zooming the circuit so that you can look it nicely from the screen. So now the problem is, let me just write it. So I require a 1 over here, D over here, and also I have seen that I require a 1 over here, and also I require a 1 over here. So just look at the slightly zoomed version. So you can see that all both the flip flops has to be made to 1, 1. So now what is the one way? If we are using a propagation, I am not going to discuss the old story, in which case without using any scan chain business, if you want to make both the lines, both the flops 1, you can do it, but you will require 2 or more patterns for that. Because to make first flip flop 1, you have to apply a C equal to 1 and apply a clock pulse. The first flip flop output will be directly equal to 1. But then at the second step, you have to make B equal to 1 and C equal B first step, C equal to 1 if you make, the first flip flop value will be 1. Next basically to make the second flip flop value equal to 1, you have to apply B equal to 1. So now if the B equal to 1, this is 1, already D is equal to 1, apply a clock pulse, the output will be 1. So 2 patterns will be extra required to settle the business of the 2 flip flops in chain. If there are more number of circuits in the chain, this problem will actually blow up. That you have to find out an extra algorithms. In fact, people have already tried it. It is a more complicated mathematical problem that if flip flops are intertwined without using any scan or set reset, how can you get to the real values required in a very short amount of time. These are more mathematical problem, but nowadays nobody uses it because the story of scan chain has come into picture. So I think you are able to appreciate that if you are not able to directly control the flip flops, you require more number of test patterns and also calculation. Like here I am calculating C equal to 1 will make flip flop 1 equal to 1, but I require some mathematical calculations to find out that B has to be also equal to 1 and in the next stage flip flop 2 will become 1. So, if the more intertwined circuit, you can find out that it is going to become a more complicated binary equation solving kind of a problem. But anyway, now we have the story of scan chain, so it is simple. So, now basically this is the story. So, now I am first connecting it to a scan chain. So, let me just, I am zooming the circuit for you. So, you just concentrate on the circuit. So, it is a scan mode. So, if you look at the scan mode, you can see that this line is cut and then this line is also cut. So, and the output of this flip flop is connected to this one and so this. So, this flip flop 1 and flip flop 2 are in a shift register mode. So, what you have to do? You have to have M equal to 1, that is test mode is equal to 1, that is this scan chain is connected, C and E are decoupled. So, the sequential part is one side, the combination part is totally decoupled. We put 1 1 here in the input and I apply 2 clock pulses. So, once you do, of course, first this one will come over here, the next clock pulse this one will go over here and this one will come over here. Simple digital design, shift register fundamentals. Now, both the flip flops are set, but I have to apply 2 clock pulses. That is what the time is being taken. So, I require 2 clock pulses to do this, but mathematical computation is very simple in this case. So, when you see for testing, optimizations are at many phases. One is the test time generation optimization, that ATPG algorithm optimization, and how much time you require to do the test plan or you have to optimize, how much time you require for that. So, in scan chain it is very simple, you first go for a combinational ATPG, already which is not a very complicated problem, then you know the values of flip flop outputs and then directly assume that I will be a shift register and I will do the problem. But if the scan chain is not there, then you have to use the combinational circuits to put the flip flops into that mode. Like in this case I have told you, first you have to make C equal to 1, then you have to make B equal to 1, C equal to 1, which will make E equal to 1 and the flip flop 2 will be 1. So, in this simple circuit still you require some backtracking. So, it is a very complicated circuit, this backtrack will be very large. So, the ATPG generation complexity will become very high. Scan chain actually solves that problem almost, because it will just, when if you have assumed that you have a scan chain, that means directly you will be able to apply the test pattern from the ATPG of a combinational circuit, which you are doing in this example. So, ATPG complexity remains same, it does not change. But what another important paradigm of complexity of testing is how much time you require to apply the test pattern. That is not actually too much solved over here, because in this case of scan chain, of course, you can apply the vectors very fast. Just I am going to tell you this, just you can look over here. If I am going by scan chain, so there is one flip flop, another flip flop, another flip flop, 1 1 I apply and I give a very fast clock pulse. When I am writing 2 clock pulses over here, the clock pulses will be very fast. But till 2 clock pulses are required, so test time is still remains a challenge for me. But if you see, if I say that I go by the previous approach, in which case I say that B equal to 1 and C equal to 1, in fact B equal to 1 and this line D equal to 1, and I am going to make flip flop 2 equal to 1. So, the clock speed cannot be that much high, because there will be a delay of this AND gate E in picture. So, it is a very big circuit, instead of this AND gate you have a large circuit. So, setting and resetting the flip flops using the combination circuit will slow down the clock. So, in case of scan, you require say 2 clock pulses in this to settle the values. In case of without a scan chain also, you will be requiring 2 clock periods to do it. But in case of without a scan chain, you will also have the delay of this AND gate. So, clock frequency will be slightly less. So, with just a scan chain, number of test patterns may remain same, but the frequency will be much higher compared to without a scan chain. So, this is one optimization we can achieve without this with a scan chain. So, scan chain actually solves the complexity of automatic test pattern generation to a great level. Secondly, another problem actually it solves is that the clock frequency can be very high. But what challenge still remains is that if there are hundreds of flops in a chain, you have to apply 100 clock periods to do it. So, ATPG application complexity, that is test pattern application complexity still remains, which we are going to solve in the next series of lectures. So, anyway, so now if you look at the circuit, so what they have done, they have applied 1 and 1. So, this flip flop is now 1, this flip flop is now 1, we applied this one, the values have been settled. Now, we are going to simply apply your test patterns. So, what they are applying over here? So, this flip flop is 1, this flip flop is 1. So, you have to apply A equal to 1. So, A equal to 1 means it is D, and of course, if the value of B equal to 1, this one already we have seen this, you can just see that automatically you are going to get 1 and you are going to get the test. So, what is the test pattern here? A equal to 1, B equal to 1 and C equal to X. But before that, this scan has to be settled as 1 and 1. So, there are 2 test patterns, basically in 3 clock periods will be required, in fact 2 clock periods and 1 extra will be required to test it. So, 2 clock periods will be required to settle the flops to 1 1, and finally, you have to apply 1 and a 1, the real test pattern, and your circuit will be tested as D at the output. Now, what? So, This brings us to a very concise representation of VLSI testing, which we will use to do for medium to fairly complex circuits, say around 20 years, around 10 years back or so forth. Now, what are the challenges we are going to face, or what are the challenges we have faced, which we will be trying to address over here. First challenge is, if the circuit is very, very large, say we have tens of millions of gates, so at least some 1,100 faults will require test patterns, because one test pattern can solve multiple faults we have seen. But still you require some hundreds of thousands of test patterns to be applied to do the testing. So if you have NOCs and SOCs of that challenge, it is impossible to even at the same fault model, you apply test patterns and you can do it. Still the number of test patterns will be so high that we will not be able to do it. So what is the optimization? Some people will actually try to find out which are the very good test patterns, that if there are 100 test patterns, first test pattern detects 50 faults. The last 2-3 test patterns will detect only 1 or 2 very difficult to test faults. So I have to compromise. So I will select only such test patterns which can test huge number of patterns and slightly compromise on the coverage complexity, because there is no way I can go for 100% testing and spend hours in the tester and make your chip make $1,000 a simple chip for simple maybe a mobile processing unit. I have to have some quality control, and well I have to go for the cost matrix, because mostly when you are talking about VLSI systems, major area is consumer electronics. So where we do not require a very rigorous part, we require some quality of service of course, but not as a rocket science. But we have to make it affordable, because nobody can purchase some 1 lakh rupees mobile phone and which we say that it will never hang. Rather I will prefer to purchase a 10,000 rupees mobile phone, which may say have some issues, maybe in 1 month some issue may come up. That is the basic philosophy, that where you have to bring a trade off. So one challenge is, how can you bring down the ATPG, or means number of test patterns, and still we have to have minimum compromise in coverage. Secondly, about the scan chain. So if you can see, the scan chain basically, if you make a very long scan chain, so the time to insert the test pattern in the shift ratio will be very, very high. So what I can do? Can I partition the scan chain? Can I put some of the, this is a partial scan, can I put some of the flops in partial mode and some of the in non-partial, means some of the flops will be in scan and some will leave it as it is, so that at least some area is saved, as well as at the same time I can have less time to push in the test patterns, because now instead of one chain I will have many parallel chains to do it. But many parallel chains mean at the same time many pinouts. So I cannot have 100 parallel scan chain into picture. So how will I make a trade off? Secondly, fault model. So if there is a circuit with 1 million lines, so there will be 2n or 2 million faults in the stacked fault model, or even if you are having a fault model in the gate level, that will also be very, very high. So what I can do is that I have to go at abstraction level. So what is an abstraction level? Abstraction level means I will take block as an adder, I will take block as a multiplier, I will take block as a multiplexer, and I will have some fault model at that abstraction level. I will not go into the internals of the, like for example, here I am not going into the internals of the gates. Rather I am checking whether the lines have no stacked fault or something like that. I am not bothered about the internals. But if the lines are also very high, what I do? Then again I actually make a side U-turn, that I take blocks and I find out that whether blocks are operating properly or not. It is something like moving from structural test to some kind of a functional test, but at a very, very abstract level, like an adder, a multiplexer, an ALU, simple to that. So they are actually called testing at high level fault models. Then again, everything I am going to now not go at a gate level. I will go for everything at the RTL level, the register transfer level, that at block level. So can I go for some abstraction to solve it? So basically what we are going to see, what optimizations can be done to high level synthesis for high level circuits or very complex circuits like NOCs and SOCs. Can I have a very abstract fault model? Can I do the testing at a much higher level of abstraction so that I can do at the block level? At the same time, how can I reduce the number of test patterns? Because this RTL or high level test pattern problem actually is very recent, but before that people tried to optimize how can I bring down the number of test patterns with slight compromise. How can I optimize on the number of scan chains so that I have minimum pinouts extra, but still I can do the scan chains very fast. So all these things actually will be required to do test at a circuits of higher complexity, which will be the main focus of the course from the lectures which will come up. So these first two lectures just gave you a brief coverage of what is VLSI testing, what is the philosophy, what people had done say about 10 to 15 years back, and what needs to be improved. So that idea I have tried to give you, because we want to make this course a self-contained course. And we don't want you to go back and again listen to lectures or books on CAD for VLSI or VLSI testing. So basic philosophy we have built. Now we will try to improvise on that and see how more complexity can be handled. Thank you.